All right. We will start with chapter 24, which is transport layer protocols. And as always, before we start, the comment section are open. If I say something wrong and you want to correct me, just mention the minute and the second, and correct me. Or if you have more things to add, or you want to elaborate or anything, just also elaborate and do whatever you want in the comment section so others can benefit from your knowledge. Okay, let's start. Outline, introduction, user datagram protocol, UDP, and transmission control protocol, TCP. The UDP is connectionless and TCP is connection oriented. Introduction. Okay. In chapter 23, we discussed the general principle behind the transport layer. In this chapter, we will concentrate on transport protocol in the internet. And here we have the known photo, the figure that we have been using. Here, he mentioned here like, where is it? Transport layer, TCP, and UDP. So it says in the transport layer, we will focus on them more. So TCP, transmission control protocol, is a connection-oriented, reliable protocol. Reliable, which means it's got acknowledgements, and connection-oriented, which means it's the two sides can send to each other. Unlike UDP, which is user datagram protocol, is connectionless, which means one side only can send, and reliable, no acknowledgement. Transport protocol. SCTP, stream control transmission protocol, is a new transmission layer protocol designed to combine some of the features of the UDP and TCP in an effort to create a better protocol for multimedia communication. I guess we won't focus on this type. We'll focus on the TCP and UDP. Port numbers. Transport layer provides process-to-process communication. As we said, this protocol uses port numbers to accomplish this. Port number provide end-to-end address at the transport layer and allow multiplexing and demultiplexing at this layer. Here are some well-known ports used with UDP and also TCP. I will highlight them. Like here, for example, echo, it's used in UDP, TCP, and SCTP, and you have the description for it and the number of the ports. I guess it's important to know the port number 20, which is FTP data, and it's not used in UDP because it need a connection oriented. Also, FTP 21, which is port 21, you need to know where it's used and the name of it or the description. Also, telnet is important. SMTP that we took in the emails, I guess it's important. DNS, know the port of them, know the name, know the description, know where it's used, and so on. It's an important. And also HTTP, of course, with port number 80 is important. And we can see that most of them the UDP does not cover, or we can't use with UDP. User datagram protocol, UDP. It's connectionless and reliable transport protocol. Very simple protocol using a minimum of overhead. Suitable to send a small message and does not care much about reliability. User datagram. UDP packets called user datagram, so know the name of it, user datagram. They have a fixed size of the header of 8 bits. The header of the UDP is fixed size, made of 4 fields, each of 2 bytes, which means 16 bits. The byte contains 8 bits. Okay, so the header is 8, so it's constant, and the remaining is with the data. So this is the user UDP user datagram. The first one is source port number, then destination port number, then total length, then the checksum that we use in control error control, the header format. Okay, like for example, the following is a UDP header. Okay, in hexadecimal format. What is the source port number? What is the destination port number? What is the length of the UDP? What is the length of the data? As we said, the length of the header he won't ask you because it's constant, 8 bits. So you won't need this information, but we will use this information to know the length of the data. Like here, what is the source port number? It will be the first four. This is the nice. This is the source port number. Destination port number will be the second four. Destination port number 00D. The total length of the user datagram. The user datagram should be what? 16. The length 16-bit, right? What is the length of the data? The length of the data will be the total length. It should be 32, I guess, minus the 8 bits because the header is constant, and you will get the data. Total length. Oh, the total length here. So it will be the 001C. And of course, the last one would be the checksum. He didn't ask for it here, but it's 001C. It's the checksum. And how do you get the length of the data? Which is the total length, not the total length, like the 32, because it starts from 0 till 32, so it's the 32 bits minus 8, which is the header. We will get the length of the data. Okay, so here is the solution. He converted it, means that the source port number is, here is the destination, here is the length. So he convert the third fourth hexadecimal to find the length of the UDP as 28. So the total length 001C, when he converted it to decimal, it shows 28. So 28 minus 8, which is the constant header size, it's 20 bytes at the end. Okay. UDP services. UDP services, process-to-process communication, connectionless serverless, flow control, error control. It got no error control, no flow control. Connectionless is independent datagram. Checksum, it's optional in UDP, and it's mandatory is in TCP. Checksum does not know. طيب. UDP provide process-to-process uses socket address. Okay, we know this. Okay. And here more details like pseudo header for checksum calculation, the pseudo header, and this is the header that we saw, the source, destination, length, checksum. Here is the data. Here is the optional pseudocode. When if you add the checksum, you will have this new. So it is optional for checksum, the pseudo header. Okay. UDP applications. UDP is preferable for some applications. So because it's connectionless, it's I guess good in live streaming or let's read. For some application, the reasons services may have affected. The application does designers sometimes need to comprise to the optimal the delivery and more can make sense. 3 day. Okay, high speed and low cost conflict with each other. Can benefit more from UDP. What can benefit more is the DNS. SMTP cannot benefit more. A real-time interactive act such as CAB, yes, it can benefit from the UDP because sometimes we don't care about the missing frames or etc. Here is an example. A client-server application such as DNS uses the server services of UDP because a clients need to send a short request to receive a quick response and can each fit in one user datagram. Since only one message is exchanged in each direction, the connectionless feature is not an issue. The client or server does not worry the message that the message are delivered out of order. Okay, so we don't care. A client server application such as SMTP, it's complex and difficult, so I guess it won't be appropriate. A user can be, yeah, if you have an email, the order is important, so the UDP connectionless is not an appropriate connectionless may create a problem. Okay. arrive out of order, and this is bad. Out of order, and this is bad because in an email we care about the order. Cannot be able to record the business. Okay, so it's not useful in the SMTP. And also assume we download a very large text file from an internet. Also here, I guess UDP is not suitable because we care about the uh, order here. Provide we don't part of the file to be missing or corrupted. And also, we don't want it to be missing or corrupted. Also, the order is important. The delay created between the deliveries of the packets is not overriding concern for us. We wait until the whole file is composed before looking at it. Okay. A real-time iterative application Skype here is UDP better because sometimes we don't care about the frames if it is um, missing or something. I won't like make the user notice. But if I'm using a reliable connection, he will notice, so it will break the live stream. Okay. Audio and video are divided into frames, supposed to be recent, corrupted, or lost frames, synchronized the whole time. So, okay. The viewer suddenly seeks blank screen and need to wait until the second transmission arrives because now we care. So the UDP here is better. This is not tolerate. Okay. However, if a small part of this screen is sent using the one signal user datagram, UDP can easily ignore it. That's about it. So most okay, UDP here is as I said before in Skype or live stream or etc. UDP is better. Is good. Is a good application. Okay. Now with the next part, TCP. A transmission control protocol is a connection-oriented, reliable. Okay. Connectionless, connection-oriented, I mean, which means it has a flow control, error control, reliable protocol, provide connection-oriented and explicitly define connection, establish data transfer and connection termination, handshake. TCP uses a combination of go back in and selective repeat protocols to provide reliability. Okay. TCP services. We have many services, process to process, stream delivery, multiplex and demultiplex, oriented, reliable service. Okay. Here it shows you a window like a buffer and so on. What else? Example 27. Suppose a TCP connection is transferring a file of 5,000 bytes. The first byte is number 1,000. 10,001. What are the sequence number for each segment of the data sent carry 1,000 bytes? Okay, the solution is a sequence number from 1001. The range will be from 1001 till 11,000 and so on. We will increase by 1 and we add 1,000 and so on. So in the range we include the first range here. We include it. And then we add 1,000 to it, it will be 11,000 and so on. We will keep going. So we will have 5 segments covering 5,000 bytes. Segments, a packet TCP is called segment, so you can memorize it. The header from 20 to 60 bytes. And the header consists of 32 bits. We have the source port, destination, sequence number, 22 bits, and acknowledgement number. And also we have a checksum and it's mandatory in TCP, urgent pointer, window size, and also these are important. The URG, acknowledgement push, and SYN, WFIN, yeah. We will know more about them, and here optional padding for 40 bytes. This is a segment of the TCP. Here it's explaining more the ones are here, which is URG, urgent pointer is valid, acknowledgement, push, request for push, reset for the connection, and synchronize sequence numbers, and terminate the connection. Okay, so it's 6 bits, and these are the Here we have a header. Let me see. And a pseudo header is added because it's always be added because the checksum is mandatory in TCP. Unlike UDP, it's optional. So all the rest are the same: source, destination, sequence number, acknowledgement, reserved, control, window, and urgent point, etc. TCP connection that requires 3 phases: connection establish, handshakes, connection termination, handshakes, data transfer. Okay. This will start a logical path between the source and destination. All of the segments belonging to a message are then sent over this logical path. Okay. TCP uses the services of IP to deliver individual segments to the receiver, but it controls the connection itself. So we have a flow control, error control, flow control to not overwhelm the receiver, error control to make sure everything is fine, congestion control, I guess, to make sure the traffic is I forget. I guess to make sure the traffic is not busy. I don't know. Connection established. Okay, the first thing, connection established, we mean the 3 handshakes. So TCP, usually it's a full duplex mode. This implies that each party must initialize communication to get approval from the other party before any data are transmitted or transferred. The connection established in TCP is called 3-way handshake. Okay, the client wants to make a connection with another application program called the server. The TCP as the transport layer. The process starts with the server. The server program tells the TCP that it is ready to accept a connection. This request is called passive open. Passive open. The TCP server is ready to accept the connection. It cannot make a connection itself. Okay, the server cannot make, only the client. The client program issue a request an active open. So the client is an active open, the server is a passive open. A client that wishes to connect to TCP to connect. Okay. 3-way handshakes. Step 1. The client sends the first segment and SYN segment to the server for synchronization of sequence number by setting the SYN flag. So SYN flag will be 1, not 0. 1 which means it's active or available or so on. Yeah, active, I guess, or valid. 0 mean it's not valid, inactive, etc. Displaying the first sequence number. So we have to display the first sequence to know, so that we know the acknowledgement sequence number and so on. It must be in order, you know. It's a connection oriented. It is random number usually called the initial sequence number, ISN. Note that the segment does not contain an acknowledgement number. So it does not contain an acknowledgement number. It's the first one. It does not define the window size either. So not yet the W window, not defined. The SYN segment is a control segment and carries no data. So it carries no data. However, it's consumed one sequence number. This is important. The SYN does not have any data, but it's consumed one sequence number because it needs to be acknowledged. Okay. We can say that the SYN segment carries no imaginary byte. Okay. Then the second, which is the server, will send the sequence, the SYN flag, and the acknowledgement to tell the client that, oh, I received your SYN flag also. So first, the SYN flag to the server will initialize the sequence number for numbering the bytes. So it's from its side also the receiver will have the sequence number. The SYN flag is set displaying the first sequence number. Second, to also acknowledge the sequence number received from the client by setting the acknowledgement flag, displaying the next sequence number it expected. That let's say the client say the sequence number is 32. Now it will be here the 33 from the server. It will acknowledge 33. Third, define the receive window size. So it will define the window size, RWND. So it will define the receive window size. Since the segment is playing the role of SYN segment, it needs to be acknowledged. So also the SYN will be acknowledged from, it therefore consumes one sequence number. As we said, the SYN consumes one sequence numbers and carry no data. And now it will need to be acknowledged by the client. Okay. The client set the third segment, the last one, an acknowledgement to tell the server, oh, I received your SYN, and also acknowledge the acknowledgement. It's acknowledged that the receptor of the second segment, acknowledgement flag, acknowledge number field. It also defines the window size now by itself, the RUWND. So it's defined from the server and from the clients. Note that some implementation allow the third segment in the data connection phase to carry the first chunk of data. So I can acknowledge here, plus maybe I can give some data. Some implementations provide this, and if I want to do this, I will have also to put the push flag, because I need to give a data now. And this will illustrate many things now. This is very important. A will, which means acknowledgement flag, S, which means send flag. So an active open here in a passive open, as we illustrated. We have a sequence number randomly, it's 8,000, and with the synchronized, getting one. So here we'll have one, the rest are zeros, okay? The rest are zeros. Then, when the receiver or the server receive the send flag, it will create also a sequence number from its side and will acknowledge the next. It will acknowledge by getting the sequence number plus one, as you can see, 8001, and also, as we said, it will define the window size by itself, 5000, and we'll have the acknowledgement for this synchronized, and also it will synchronize itself. The server is synchronized also. Now, the client will take the sequence number 8001. It will acknowledge 15001 because it was received from here. So it will add one and to acknowledge it. And this is the acknowledgement. And also it will define its window size. It's 10,000. So the server window size is 5,000. The client is window size is 10,000. Okay, send floating attack, as we said, denial of services. Yeah, we discussed it. Yes, denial of services attack. Send floating, which means sending many send floating requests, but we are not actually real users, so we just sending fake send floating. It will overwhelm the server. You can say this is the, in short, what it does. Yani. This happens when one or more attackers send a large number of send segments to the server by faking the source IP address. The server, assuming that the client are issuing an active open, allocate the necessary resources. The TCP receiver then sends send plus acknowledgement, the second handshake, to the fake clients. So it will lose its resources. When now a real user come, it has no space because I got many requests. Many fake requests I have to deal with. When the server waits for a third leg, for the third leg of the handshaking processes, however, resources are allocated without being used. The request more valid requests from valid clients. You see, the self-loading attack belongs to a group of security attacks called denial of service attack, as we know. Some implementation of TCP have strategies to prevent the SYN attack. Maybe they can limit the connection requests. Other can filter out datagrams, so unwanted they can be filtered. One recent strategy is to postpone resource allocate until the server can verify that the connection request is coming from the valid IP address by using the cookie. The cookie, which means, as we illustrated earlier, it was like the one that saves user logins and data and so on. So if you have the cookies already, which means you are a valid user. So yeah, this is a third way to deal with the self-loading attack. Now, with data transfer, after we did the handshake, we want to transfer the data. This is a biggie bagging because each one of them is sending data now and acknowledging. Now, sending data and acknowledging. Here, it's sending data, the data, and also acknowledging the previous segments and so on. Here it should, there is a mistake here. It should have B also. Okay, like this, it will have P here. So be careful of this. We will have P here. Okay, there is a mistake here. And the rest are clear, I guess. Here we have an acknowledgement after the connection established. Now we make an acknowledgement. We make a push flag also as one. The rest are zero. We don't need them. Push as one. Whenever you have data to send, make the flag push as one. The sequence is 8001 and an acknowledgement is 15,001 after we made the connection established. Okay. It will go to the receiver. I want to send another thing. It will be 9001 because the last one was 9000. I will add one to it. It will be 9001. Now it's 10,000 and 10,000. Okay. After I send it, I get the acknowledgement from the server, acknowledgement 10,001, and it will acknowledge this and this. So it's a cumulative acknowledgement, okay? So when I receive acknowledgement 10,001, it means 10,000 have been received and everything before it have been received. So all of this have been received, all of this have been received. It will set the window also as 3,000, and also it will have a P here, P flag as here, because it's sending a data currently. It's sending 2,000 bytes of data or bits of data. Now in acknowledging, it will be the last bits has been sent, which is 17,000 plus 1. So the acknowledgement will be 17,001, telling the server like send the next data from 70,001. And it will acknowledge, and without the P flag, okay, without the P flag, because there is no data I'm sending now. And I'm setting my window to 10,000. Yeah, 10,000 as a size of my of the client window. Okay, here when it comes to establishing or termination, it will be the same thing. You will have a fin flag active from here, and here fin, and acknowledging that I received the previous fin, and here also acknowledging that I have received the fin flag from the server. And this is how actually establishing the connection and termination connection, both of them are similar to this. We have to set the fin flag as 1 and the rest are zeros, and also the acknowledgement, of course. Keep it 1 always, يعني, because it's a connection oriented. Here acknowledgement for the previous fin or the segment in general, and now I'm sending also a fin as 1, and now the client sending the final acknowledgement that I have received your previous packet that contains the fin to terminate the connection. There is also have close, a concept called have close, when one party is closed but the other keeps sending data until he finishes, then he closed the yes, until he finishes, and then he closed the data from his side. So here I terminate with the fin. Here I acknowledged but without the fin flag. So now acknowledgement from the client to server, data segment from server to client. So only the now I didn't terminate immediately. I didn't write the F, the fin flag. I didn't set it to 1, but I acknowledged that I have received your request, client. I have received your requests. So I know that you want to close the connection, but still I get things or something. So maybe here during this period he can send data and so on. And when he finish, he will set the fin flag to 1 with the acknowledgement, and then the receiver will send the final acknowledgement telling the server that, oh, I have received your previous segment that contains the fin, and now connection is closed. Okay, now with the last part with this chapter, and then we will have the client server programming. It will be, okay, we took this and I told you there is a problem here. It should have P. Here it should have P because we have data. And this, the arrow is wrong. It should be here. Yeah, small details. And I says it push flag whenever you have data. Whenever you have data, set the push flag to 1. Whenever you have data, set push flag to 1, and so on. Connection and termination. Yeah, here's explaining termination, and also the same thing with the establish and termination. Same thing. So we already illustrated this. They have close also. Window in TCP. TCP uses 2 windows, send window and receive window, for each direction of the data transfer, which means 4 windows. We have 4 windows because they are a bidirectional communication. Both parties can send and acknowledge. So they can send data and then acknowledge at the same time, okay? To make this discussion simple, we make an unrealistic assumption that communication is only in directional So it's from one way somehow. To make it easy to illustrate, I guess, say from client to server, the bidirectional communication can be done using the two in-directional communication with piggybacking. So here we just assume that it is unidirectional in order to make it easy to explain. Send window in TCP. So we have the left wall, which is this. We have three cases, opening, closing, and shrinking. Whenever the window goes to right steps, it opens, and it shrinks whenever it's go to the left of the right wall. Whenever it's go to the left, it shrink. Window says it's shrinking, and whenever the left wall goes to the right, it's closing. All right. What is the concept here? Here the window size can be calculated by the original bytes minus bytes received. Okay. And same thing, close when it's go to right, and here it's open, so there is no shrink as I can see in the receive window in TCP. Okay. Flow control balances the. All right, flow control balances the rate of produce creates, as we said before. TCP separates flow control and from error control, of course. We will discuss flow control, ignoring error control. We assume that the logical channel between the sending and receiving TCP is error-free, so there is no error. We illustrate this like he sent data to this push. Here it's pull, so it's a request. Whenever the consumer feel it's overwhelmed or almost getting full, it will tell via flow control. It will tell the producer to make it slow to generate data or send data. Same thing with here. If I'm sending data, here he can tell me via the flow control to less speed sending data or something. And here we don't need flow control because it's a push, it's a pull, so it's a request from the receiver side. Here is an example. We have the sequence number 100, start with 100. The window size is 800. Send acknowledgement, and here also says 800. Here is giving, he's telling the client that, oh, my size is 800. So the server telling the client, window size is set. Then he's telling the server that my window size is 2000. Sequence number 101. So it will send here 200 bytes. So 101 and 201 till 301. So here there is 200 bytes received, okay, in the server size. So the window is 600 because 800 was free. Now 800 minus 200, it's 600. The 600 are free from 301 till 801. Okay, during this period, it consumed some of the 200 bytes. So now it says 300 bytes received and 100 bytes consumes. So 100 bytes consumes, it will start here from 201, and it will decrease, like it's received 300. So minus 600 minus 300, it will be 300, okay? But why it's mentioned here 400? Because 100 bytes, it's already consumed from here. So if it's consumed, oh, I have more space. So I have 400 space still, although I received 300, okay? So currently the window, it will acknowledge, of course, on the right side, on the left side, I mean, the client, it will acknowledgement, oh, I have received the thing. My window now is 400. And that's it. Window closes and opens, Windows opens, and so on. So it's stop here. It says here 200 bytes consumed. So these 200 and 300 consumed, it will start from 400. And we have 600 because 400 plus 200, because we have free space, it will be 600. Maybe you need to review like here. This is the most important thing. I focused on the right and the left side. like this, the sender, the sends, okay? But if you look here also, it's important to have to know how the sequence numbers are generated, what is the next sequence number, how to acknowledge, and so on. So the middle part is important. Error control, this means reliable, okay? Deliver entire stream to the application program. Lost or duplicated. Yeah, it's telling you here what's the job of the error control. And the tool of it is checksum, acknowledgement, and timeout. This is like the ways that it can know. We have TCP rules for generating acknowledgements. Okay. Actually, you need to read this very carefully. I will try to highlight and illustrate with the figures here as much as I can, but you have to read and know. You have to read and memorize and understand these rules. So here it says piggybacking and acknowledgement that gives the next sequence number to expect it to receive, as we have been used to. When it has no data to send, it will delay its sending to another segment or until period of time normally. So this I'm just giving you what you have to focus on, I guess. Immediately it will send. And here too, in order, acknowledgement segments at a time, congestion. Okay, so let's see from an example. Rule one. I guess it says like when you send any sequence, send an acknowledgement with it. Here it's the rule one, the same. Here is the rule two. Rule two that says if you have no data to send and the previous segment had already been acknowledged, the receiver delays sending acknowledgement until a specific amount of time. So when the time out, it sends the acknowledgement because it have no data to send and only one segment have been received. But if two segments have been received and I have no data now, I will send immediately an acknowledgement. So either the case is the first rule is just acknowledgement concept, nothing new. The second case, it says like when you have no data, just wait for another segment. Like the minimum is two segments. Like if it's one segment is received, do not just immediately send acknowledgement. Maybe you will get data or maybe you will get another segment and so on. So it won't send any acknowledgement. But once the time out, the time is reached or the time finishes, it will immediately send the acknowledgement. But what if it receives the other segment here? Also, after it receives it, it will immediately provide an acknowledgement. Like here, the other example, it received two segments and it has no data to send, so it just acknowledge immediately after it received two segments. And this is the rule three. The rule two, it means you have to wait until other segments received, then you acknowledge both. What else? And here, when you acknowledge 7001, which means this one, you acknowledge it, you acknowledge everything before it. So it's a cumulative acknowledgement. Here we have rule 4 that says when a segment arrived with an out of order sequence number that is higher than expected, the receive immediately send an acknowledgement announcing the sequence number for the next expected segments. So fast retransmission of the missing segment. So let's see here. Here is normal rule number 3. Here it's lost, so it does not receive to the server. And here he received a higher block, so he did not receive this. So he received the higher block. He will immediately give an acknowledgement for 701 to tell them, oh, I did receive the previous one. So he will immediately give them back to the one and will keep going. It will not acknowledge like give me 801. It's already there. It will tell them give me the 901, the 901, which is the next one. It will be here. Okay, so the next one, and this is the rule of when missing segment arrives, the receiver sent the acknowledgement to announce the next sequence number expected. The next expected, so not the one that I already have received. No, the next one. that I'm expecting to receive. Okay, this is node number 5, I mean, and the 4 is the out of order. When you receive something bigger than you expected, you immediately send an acknowledgement to the lower party or the smaller one in order to make them know that oh, I didn't receive the smaller segment and I receive a bigger segment. Fast retransmission. It's a special case. You have first duplicate, second duplicate, third duplicate. So let me try to remember this. Here is the normal rule number one, here number 2, I guess, or 3. When you receive give acknowledgement to 2 segments, here that is lost. That is lost, and then you ask for the and you receive here a higher number, a higher segment. So you will be expecting to send an acknowledgement for the lower one, which is 301, the one before this, in order to tell the sender to give me this. So when I send it, it does ignore me and send the next one here. And when I send it again, I want this, the smaller one. He ignored me and sent this again, the next one. And finally, the third one, now he obey and send me the datagram that I want. And then I use the rule number 5 in order to tell them, oh, we are here now, to tell them the next one I expected. So here is a special case. He tells like whenever you have 3 duplicate, the client will obey at the end to send the data missing that you are looking for. But with the first and second, he can ignore it. You know, he can ignore it and keep sending the next packets. But whenever he receives three duplicates acknowledgements, he immediately sends that sequence number. It's like a special case. Okay. Lost acknowledgement. Lost acknowledgement. So here it's lost acknowledgement. He will send the next and the next. Yes. Here the time did not finish. Okay. So when I missed the acknowledgement number 701, but the client will keep sending. Okay, he don't care. He will keep sending. And now when he give 2 segments, each 2 segments will correspond to another acknowledgement. The first one, the first 2 segments, the first acknowledge did not receive. Then when I sent also another 2 segments, that acknowledgement have been received. So now when I receive this acknowledgement, which says 901, which means I have he's telling me that he received all of these, although we missed the previous segment. It's a cumulative, okay? But here is the rule number 6. If a duplicate segment arrives, like here, for example, he sends the first one, the second one, then he got nothing to send, and the time is up, okay? And I missed the acknowledgement. So I'm saying like I'm thinking like, oh, he did not receive this or this, okay? So I will resend them again, all of them. So whenever he sent the first one, he will give me the acknowledgement for the next one that he expected. Okay? So he will give it to me. Oh, then he know like he received this and also this. So I do not have to retransmit this one again. From this one, I know already that he have been already received from 700 till and all the previous ones. And this is the rule number 6. If the duplicate segments arrive, the receiver discards the segments, but immediately sends an acknowledgement indicating the next in order segments expected. So it will tell him, oh, I expect 701, which means I have received everything you have sent here. Okay. TCP cognition control. TCP uses 2 different policies to handle the congestion in the network, to control the number of the segments, to transmit. TCP uses another variable called a congestion window, CWND, along with the RWND. To know the actual window size, just take the minimum between the two. So if this is 5, so if this is so if this is 5 and this is 4, what about application? Okay, and this is 4, so the actual window size will be 4. Congestion detection will be through timeout or with no acknowledgement or receiving 3 duplicate acknowledgements. So if he asks you how to know if there is a congestion detection via these two ways. Congestion policy algorithm. TCP is generally policy for handling congestion. It's based on 3 algorithms. So congestion policy algorithm based on the slow start, congestion avoidance, and fast recovery. We'll know more about them now. The slow start is exponentially increase. Exponential increase, which means 2 to the power 0, then here 2 to the power 1, then here 2 to the power 2, then here 2 to the power 3, and so on. So here it was 1, 0 to the power 1, the CWND, okay? So here it was 1, now it's 2, sending 2, now it's 4, sending 4, and get 4 acknowledgement, now it's 8, so it will send 8, and get 8 acknowledgement, and so on. This is the slow start, exponential increase. Then the congestion avoidance, the second phase. You can say this like it's the first step or something in the congestion policy algorithm. Okay, the congestion algorithm. First step, you can say it's a slow start, exponential increase. This is, you can say it's a second step, addictive increase by 1. So it's a start by 4. It will be 5 here. It will be in a 4, 5, 6, 7, and so on. So it will increase by 1 each time. So this is the second step, which is congestion avoidance that comes after the slow start. You have here wow, we have many things. We have there are 3 versions of TCP. Tahoe TCP, Reno TCP, New Reno TCP. What else? An example of it, yes, is this. All right, it's last 2 slides, and then I will show external photos that I think it's important, but I will try to explain this. It will start from here, like this thresholds at the top at an initial phase. Then it will start from here, from 0. It will start by what? SSS, which means slow start, which means exponential. So it will start from 1, then exponential. It will go to 2, then 4, then 8. And we have like events. We have 2 events, 3 duplicate acknowledgement and timeout. This is the first event, which is timeout. Whenever you reach a timeout, you will take the current threshold, which now it says 8, and you will divide it by 2. It will be 4. So at the first stage, the threshold was the maximum. Now ignore it. The threshold become here 8. The new threshold now 8 over 2 will be 4. So now here is the 4. Look at the new threshold, which is 4. And you will come back to the starting point and also back to the slow start, which means exponential. 0, 2, and then 4. And now when you reach the threshold, you will change from slow start to congestion avoidance, which means you will start to add 1. Okay, you can see here is the labels meaning. Okay, CA, which means congestion avoidance. After you reach the threshold, you will start to add 1. So here it's 4, 5, 6, 7, 8, 9, 10, 11, 12. And assume here we have received the second event, like we have 2 events in this example, Tahoe TCP, which mean 3 duplicates acknowledgements. Okay, what you will do now, same thing, current place over 2. So current place is 12 over 2, which means 6. The new threshold will be 6. Look at this. The new threshold will be 6. And now this pointer will go back to the initial point as we start. All the initial points are the same. Now, again, slow start, exponential from 0, from 1 to 2 to 4, then to 6, because we can't go above the threshold suddenly to 8. Okay, so come here to 6, or the nearest thing to the threshold or the threshold itself. Then after this threshold, again we'll go to congestion avoidance. The second step will increase by one, to increase by one, by one, by one, and so on. So here the question will come like, oh, you have received the timeout. What should you happen? Oh, you will say the current state over 2 will be the new threshold. So if I stop in 8, what is the new threshold? Oh, it's 4, because 8 over 2 is 4. And what shall I do with my current progress? Oh, bring it back to an initial state. Then start with the slow start, which is the exponential part, which I illustrated here. Slow start, exponential, okay? Then after you reach the threshold, you will change from slow start to congestion avoidance, which is +1, as we'll explain here. So here it's keep +1, +1, +1. Then he will ask you, oh, what if you receive 3 duplicate acknowledgements? Oh, this is another event, another problem. What are you going to do if you receive the three duplicate acknowledgements in the progress of 12? What is the new threshold? You will say 12 over 2, it's 6. So the 6 is the new threshold. And what is going to happen with our progress? It will come down to an initial point. Then I will start again with the slow start, exponential. I will keep going until I reach the threshold. Then I will keep going with the slow start infinitely, or until I face another event like this, timeout or 3 duplicate acknowledgement, and I will do the same process and so on. I hope it's clear. This is with Tahoe TCP, and here is the rule. The threshold must be bigger than or equal to the CWND. All right. So I hope it's clear. This is with Tahoe TCP. Now with Reno TCP, we have 3 events. We have duplicates, timeout, and a new acknowledgement. And there are some differences. We have the new thing, fast recovery. The rest are the same, exactly the same. You don't have anything. Yes, as I explained here, threshold is the point that you change from slow start to congestion avoidance, okay? From exponential to +1, okay? It's from when you hit the threshold, okay? Here is the same thing. When you reach the timeout event, what are you going to do? Oh, the current progress, which is over 2, which is 4. This is the new threshold. Then you will go back to the start. Let's go slow start, which is exponential. Let's go 2, then 4. Oh, I have received reached the threshold. Now I will go for the congestion avoidance, +1, +1, +1. Oh, I received 3 duplicate acknowledgements. What's happened when I receive the 3 duplicate acknowledgements? I won't go back when I receive in Reno TCP. It's not like this. I won't go back to the initial start. I will enter a phase called fast recovery, and it's simple. Like for example, when you receive the second event, like 3 duplicate acknowledgements, what are you going to do? The current progress is 12, right? 12 over 2 is 6. The new threshold is 6. You will start this not from the initial, not from down. You will start from the threshold +3. So what is it? Threshold is 6 +3, it is 9. So here is the 9. Oh, I will start from here. And what I'm going to do, 9, 10, I will keep plus. I will keep exponentially. Exponential or +1 this? +1, let's say. First recovery, is it a +1 or? As I can see, from 9 to 1 to 10, then the 12. Yes, I guess it's like the slow start, so it will be exponentially, okay? So you will keep adding exponentially here, I guess. Then there is another event, as we said, the Reno TCP got 3 special events, not like the Tahoe TCP got 2 events. The third event is the new acknowledgement. What are you going to do when you receive a new acknowledgement? Just get down to the threshold and just continue as congestion avoidance. So here I received here at 12 new acknowledgement. while I'm in fast recovery. So immediately I will go back to the threshold, and now I will keep just adding one. So I am in the congestion avoidance phase. Uh, I hope it's clear. Okay. It's really complicated. Maybe you need to read the book and so on. Before I go to the programming part, so that I don't forget, there are some useful useful photos that I want to share with you, and I hope it's going to be clear because it's small. I hope it's going to be clear. Okay. Let me see. Okay. Let's see. Hmm. Hmm. Oh my God, that's maybe it's not clear, but I will try my best. Okay, let's see. What what a bad photo. Okay, this may be an important concept. Maybe you have to look at it at the book. And as I remember, there were some misunderstanding, like the student were solving it in a way, and the book is solving it in a way. But just know the example. You have to go to the book and read about this, how to get the throughput, which by this law 0.75 multiplied by W max, but over RTT. I forget actually the concept. And here also an example. Not a bad resolution, but try to try to understand it. Maybe you can take a photo for it or something. Ask your friends and so on. It's an important concept, but now I guess I forget it. Or there were many talk about this question and many ways to solve it. Uh, but whatever way you select, you will get the mark for it. So just memorize one way or understand one way. Uh, Here's the concept: is like when the when the figure look at a chainsaw or something, you will use this law or this law. So read the book about it. It's 786, I guess, in the book. Read this example. Maybe you can read this example and try to solve it. This is an important thing, I guess, in this uh, related to uh, the this chapter. Uh, yes. Let me see if I know. Yeah, when there is when it looks like a chainsaw, you use the slow. Yes, yes, yes. Okay, okay. I guess that's it for this chapter. We still have the client server. Yes, we still have the client. We explained this. Yes, socket programming using UDP connection less protocol. Okay, we have already explained the TCP, I guess, before. Uh, so yeah, it's the same thing here. We explained this. We said here, explain this also. We will import from the socket, import everything, and then server name, host name, port number 12,000, and then socket IP, INF, INET, which mean I'm using here the IPv4, and the socket diagram, which means it is UDP a protocol, not TCP. Okay. Then he asks the user for input, and of course there is no dot connect, if you remember it, because there is no handshake here. It's a connectionless protocol, and then it will send it to the server after it's encoding it and give it server name, server port, a modification message, and server port. It will receive it from the server. It will decode it, and then it will close. That's it. And from the server side, that were the client. Now from the server side, same thing, IPv4 and UDP. It will I didn't write thing here because it is the IP of the server, I guess, so it's already known by the server. Then the server port. Uh, it will immediately print the server is ready, but I remember in the TCP was there was the thing that called .listen one. Here it's not showing because it's connectionless, as we said. Here it's asked for the to receive the message from the client. Then it will decode and .upper to make it in uppercase and decode, of course. Then it will encode it and send it to the client as an encode. Yes, and that's it. For more details, as always, read the book, read the chapter of the book, read uh, the things, and understand these two. Sorry for not explaining this because I don't know. I don't know. I forget it, I guess. But it was an important thing, so just take a look at it. And yeah, that's it for chapter 24.